Hello, everyone. I'm Koji Tanabe, founder and CEO of Eyepiece. Welcome to my channel. I'm so great to be here. In this channel, Future Medical Lab, our goal is to help you understand how cutting-edge medicine, the latest breakthroughs in medical technology, will actually impact your health. We want to give you accurate, reliable information and make it all make sense. Along the way, we'll also be touching on some of today's hottest topics: longevity, age reversal, and of course, iPS cells.
I'm Kazuki, his assistant. Koji, I'm looking forward to starting this channel today. I'll be here representing the viewers, asking all the questions I think you'd want to ask about medicine and health. Let's get started. So, Koji, this is the very first episode of Future Medicine Lab. You're someone who's been on the front lines of iPS cell research, and I'd love to know, what made you decide to start a YouTube channel?
I'm 42 years old now, and I've actually never used social media or YouTube at all before. The reason I decided to start this is that I feel many people don't really perceive the latest science and technology as something accessible or close to them. Whether it's something happening in science fiction or something occurring in a completely different world, how we can feel it close to us, how it will change our daily lives, and how we can make informed decisions based on accurate information. There's still a significant lack of knowledge regarding these topics. To bridge that gap, I've decided to start this channel.
So, from a researcher's perspective, you'll be sharing information in a way that's easy for the general public to understand. For the very first video, I'm thinking we'd like to hear a lot from you, almost like a self-introduction. On this channel, we plan to continue to share the very latest medical information, presented from your unique researcher perspective. So, for all of you who are watching this video right now, all of our valued viewers, we kindly ask you to please subscribe to our channel. And if you could just hit that like button for this video, we would be truly grateful if you could help us ensure that this video reaches a wider audience. Well then, I'd like to ask you various questions. First, could you please explain your background and career up to this point in a way that's easy for our viewers to grasp?
Of course. I've loved biology since I was a little kid. My original fascination was actually with newts. You might not know this, but newts are remarkable. If you cut off their tail, it grows back. Cut off a limb, it grows back. You can even remove their eye or part of their heart, and they'll regenerate it. That was my starting point. When I went to university and was applying to postgraduate school, I wrote something like a love letter to various professors, explaining what I wanted to study. And Professor Shinya Yamanaka wrote back and said, "If you come to my lab, we might be able to do exactly that together." So I joined his lab at Kyoto University, and that's where it all began.
So that's where your career as a researcher started, right? And as you mentioned, regeneration was your core interest. What were you actually working on when you first joined his lab?
When I first joined his lab, it was truly amazing how newts, if they lost a limb, the cells in that limb would first transform into cells capable of becoming anything. So-called dedifferentiation is like reprogramming, where a hand cell, before you know it, becomes a cell that can turn into anything. My first objective with him was to do this for humans. But after a few months, he handed me a paper saying, "How about reading this?" That was the first a paper on iPS of mouse.
And from that, I was doing research to create human iPS cells.
So that's when you started getting involved in iPS cell research from that point, right? I imagine that, whilst many members of the general public are aware that iPS cells have won a Nobel Prize in the past, they may not be fully familiar with the evolution of iPS cell research from its inception to the present day. Could you give us a brief overview of how you have been involved, the research he has conducted, and the current state of progress in this field?
Just before we delve into the history of iPS cells, I'd like to explain how these types of cells came into existence. Initially, the creation of these cells capable of developing into any type of cell was made possible by the success in culturing cells from fertilized eggs outside the body. This occurred in the early 1980s, when scientists succeeded in culturing a portion of the cells from a mouse's fertilized egg outside the body. The goal at the time was to use them as a tool for experimentation. By culturing them outside the body, manipulating their genes, and then reintroducing them into an egg, researchers hoped to create animals with specific traits, thereby advancing their research. The result of this process was mouse embryonic stem cells, known as ES cells. Initially, they were used to create clones, the most famous of which was Dolly. Through genetic engineering and research into genes, the technology to transform mouse embryonic stem cells into various types of cells continued to advance and became feasible. So what about humans? As a tool, the technology to culture these egg cells outside the body was developed, and naturally, people started thinking, wait, if these cells can become various types of cells, maybe we can create various cells outside the body too. That research began, and it wasn't until the mid-1990s. Finally, the mouse research was done in the early 1980s, and by the mid-1990s, we were able to culture human embryonic stem cells outside the body while maintaining their ability to differentiate into any type of cell. These are what are known as human embryonic stem ES cells. Once we had them, the real benefit wasn't that we could suddenly start tinkering with human genes to create clones or anything like that.
The real benefit was precisely what is now called regenerative medicine. We realized that by cultivating human embryonic stem cells outside the body, while maintaining their ability to differentiate into any cell type, just like a fertilized egg, we could use them to create various organs and develop a wide range of regenerative therapies. But there were two major ethical issues. The first, to create these cells, you have to destroy a fertilized egg, and a fertilized egg, if placed in a womb, could become a child. So there was significant global debate about whether this was destroying the very foundation of human life. In the United States, under Republican administrations, this research was actually banned. Now, to be fair, the eggs being used weren't taken from existing pregnancies. They came from fertility treatments, where many eggs are fertilized, but only some are implanted. Remaining eggs, they're called surplus embryos, are stored in liquid nitrogen. When they're no longer needed, they're discarded. The argument was, if they're going to be thrown away anyway, why not use them to help people? But even so, some argued that using them still meant destroying potential human life. It was a genuine and deeply felt ethical debate. The second issue, you can't access your own fertilized egg because you already exist. So the cells available were always from someone else, which meant that if you tried to use tissues made from those cells in your own body, your immune system would reject them. What everyone really wanted was a way to create these can-become-anything cells from a patient's own body. But that seemed like science fiction. How would you even do that?
The first method that emerged was the discovery that inserting genes into cells changes their properties. For example, if you insert gene A, the cell takes on the properties of A. For example, we realized that if you insert a skin gene, it becomes a skin cell, and if you insert a nerve gene, it becomes a nerve cell. That was the first major development. And the first successful experiment in the world was when someone discovered that if you insert a muscle gene into a skin cell, it turns into muscle. So the initial idea behind iPS cells was, if we insert a gene into a normal skin cell that tricks it into thinking it's a fertilized egg, wouldn't we get a cell that behaves like a fertilized egg? And that's what researchers all over the world were trying to achieve. So, to achieve that, researchers first studied the embryonic stem, ES cells, derived from fertilized eggs, which served as the initial model to identify which genes were essential, and they discovered many such genes. His lab also initially conducted research focused on identifying those genes. The advantage of identifying these genes is that by introducing them one by one, we can determine which ones lead to the formation of iPS cells.
But, well, there are roughly 30,000 genes. So inserting them one by one would take 30,000 experiments. But that's only when just one gene is needed. If two are needed, you have to test all possible combinations of 2 out of 30,000. If 3 are needed, it's combinations of 3 out of 30,000, 4 out of 30,000 for 4, 10 out of 30,000 for 10. You'd have to conduct an infinite number of experiments. That was honestly the hardest part of finding iPS cells. So what his lab did was narrow it down. Through careful study of what genes were most important in ES cells, they identified 24 candidate genes. That's still a lot of combinations, but it was a massive improvement from 30,000. Now, at the time, the prevailing assumption was that you'd probably only need one gene. Nobody was really thinking in terms of combinations. So the team started testing the 24 genes one by one. None of them worked on their own. But then, and this is one of my favorite moments in the story, there were some leftover wells in the experiment. Someone thought, well, we have all 24 genes sitting here unused, so let's just throw them all in together. And it worked. The iPS cells appeared. That was the breakthrough. It wasn't one gene, it was a combination. And the combination existed within those 24. They now knew. Put all 24 in, and you get iPS cells. But 24 genes is more than you need. So the next question was, what's the minimum number required? But then one of my seniors came up with a brilliant idea, almost embarrassingly simple in hindsight. Instead of adding genes one by one, what if you removed them one by one from the set of 24? If a gene is truly essential, removing it should cause the process to fail. When he presented this idea to the professor, then he apparently said, well, I probably would have thought of that myself within a day or two, which, classic. But it was a genuinely elegant solution. Without it, the work would have taken an enormous amount of time. By removing genes one by one and identifying which removals caused the process to fail, they kept narrowing it down. And in under a month, they had their answer: 4 genes. These 4 genes are now known as the Yamanaka factors. And the discovery was this: if you introduce these 4 genes into virtually any cell in the body, you can reprogram that cell back into something close to a fertilized egg. A cell that can become anything.
So instead of endlessly adding combinations, the key was to subtract to find what was truly indispensable.
Exactly. You identify what's essential by finding what you simply cannot do without.
Remarkable. And in terms of timeline, how long did all of this take?
Honestly, I don't think it took that long. Not that part, at least. But on the other hand, the work of narrowing down which genes were essential to ES cells, going from 30,000 all the way down, that wasn't just his lab. Researchers all around the world contributed to that, steadily and painstakingly. If you include all of that, we're talking well over a decade. So narrowing it down to 24, confirming it worked, and then getting to 4, that part moved quickly. But the enormous effort of all the researchers who came before, the blood and tears, and honestly, some of them probably collapsed along the way, that's what this discovery is truly built on. As my professor, Shinya, has said, research is like peeling an onion, one layer at a time. Our lab peeled the final layer, but there were many people before them who peeled layer after layer, some thick, some paper thin. That's the image I get.
So iPS cells were born from the accumulated efforts of countless researchers. What an incredible story.